Okay, let's consider another example of recursion. So this is the Fibonacci number sequence. So the Fibonacci number sequence works like this. Let's get some Fibonacci numbers down here. Fibonacci. All right. So you've got 0, 1, 1, 2, 3, 5, 8, 13, 21, and so on and so forth. Now, what a useful Fibonacci number sequence program might do is you give it the sequence number and it returns the Fibonacci number in that sequence. So I'm going to write down the sequence numbers below here. So this is 0, 1, 2, 3, 4, 5, 6, 7, 8. So if I gave the sequence number of 7, what I get back is the number 13. So number 13 is the 7th number in the Fibonacci number sequence, assuming that we start counting at 0. Okay, now a recursive solution to this would be, well, why don't you see if you can take a shot at it, and you want to think about what are the base cases and what are the recursive cases, and these two right here are your base cases. You can start out with these two, and then the rest of them you can build your recursive case from. So take a moment, hit pause, and then come back and we'll figure it out together after you've tried. All right, so hit pause. Okay, so let's define our Fibonacci number here, our Fibonacci function as define, and I'll just call it fib. I don't want to spell Fibonacci. So fib, and we're going to give it a sequence number. All right, so the idea is you'd say fib 7, and you get back the number 13. That's the idea. All right, so we've got to set up a few cases here, recursive cases, and also our base case. So let me set up a con statement. And if the sequence number, if the sequence number is 0, we're going to return 0. All right, that takes care of our first base case. If the sequence number is 1, we're going to return 1. That takes care of the second base case. All right, now the recursive case. If the sequence number is greater than 1, then we're going to return the following. You know, I always watch the freshmen. Some of them have never seen the Fibonacci number sequence before, or they've forgotten it. So it's fun to see them figure out what the pattern for the Fibonacci sequence is. So the pattern is that the current number, like this one, is the sum of the previous two numbers. So we want to specify that in our Fibonacci sequence number method function calls. So it's the sum of the two previous. So it's the number 2 numbers ago in the sequence and the number one behind the current sequence number. So we're going to sum the fib of 2 numbers ago. So, whoops, minus sequence 2. Let's see here. I want to make sure I got my paren set up correctly. Minus sequence 2, and we're going to add to that the fib of minus sequence 1. Okay, so that takes care of our con statement. So this is actually a pretty short and sweet Fibonacci number sequence function. The problem with this is, well, let's think about it a little bit. Does the stack go up as we use it, stay the same, or go down as we use it? So what would your choice be here? Well, if you said that the stack goes up as we use it, you would be correct. This is not tail recursion yet. We can make it tail recursion, but at the moment, it does use the stack and also has some branching in it as well. So that's going to create problems because when you have branching, it means you need to remember more and it's going to force you to use the stack. So why don't we take a look at how to modify this so that we can make it stackless and not branching. But before that, let's just look at how bad this is. So let's try doing the Fibonacci for the number 3. Okay, so sequence number 3. Now I can look at here and tell you that sequence number 3, oh, that's not so bad. That's going to be the value of 2, but there's a bit of work that's involved in calculating that, right? So I'm going to say f of 3. Okay, so f of 3 is f of 1, 2 sequence numbers back, and f of 2. F of 1, that's a base case. That's just going to be 0. And f of 2, plus f of 2. So f of 2, well, that's going to be a recursive case. That's going to be f of 1, f of 1 plus, f of 0 plus f of 1. And these both trigger base cases. That's 0 and that's 1. So the problem with this approach is that this plus requires us to remember things, right? We have to compute this f of 1, that's 0, and store it here in the expression. Then we have to hold that in memory on the stack until we compute this branch. This f of 2 requires a similar thing. We have to hold this 0 in the stack before we can compute this expression and get to that 1. Once this 1's computed, we can compute this expression, return that result here, and then we can compute this expression. But there is memory, and unfortunately, this branching and memory explodes in a very bad way if you end up using this as your solution to the Fibonacci number sequence. Now, this is a beautiful form of recursion. It's very clear and easy to understand, but it has problems because it's going to be using up space on the stack. All right. So how do we fix this? Well, we can take this Fibonacci function and modify it so that there's some memory associated with it, and that memory will be carried along as we make calls to the Fibonacci sequence until we end up at our result. All right. Let's think about how we could write the Fibonacci in a way that we don't need to use the stack. So what if we did this? So the idea to keep in mind of the way you want to make this work is that the results that you need to get to your final computation, you're carrying with you in arguments to the function call. So what if we defined a function called fib that carried its results with it? So we're going to have a goal. This is the sequence number we'd like to reach. We're going to have a cur, which is the current sequence number that we're on. And then we're going to carry the solution to the current sequence number and the previous solution to the sequence number before current. So we're going to carry those along with us. All right. So let's try an example without writing any code. Let's try an example to see how this might work. So we'll have, let's grab those sequence numbers again. So, and Fibonacci numbers. So we have 0, 1, 1, 2, 3, 5. All right. This is sequence number 0, 1, 2, 3, 4, 5. Okay. So let's do Fibonacci of 4. All right. So Fibonacci of 4. So the way we would use this solution, this function, which calls to the function carry partial solutions with us, so we don't have to use the stack, would be something like this. Fib, our goal is 4, our current sequence number is 0, and the solution to 0 is 0, and the previous solution to the previous sequence number, it doesn't really matter, but let's just say it's 0 to make math, we'll call this a special case. Okay, so in order to get to the 4, we're going to make another recursive call, and we're just going to increment current. All right, so we went from 0 to 1, that incremented current. Now, the solution to current is also a special case. That's 1. We know that's just how you get things rolling in this with Fibonacci numbers. These first two are special. All right. And the previous solution, again, we can say that's a special case, that's 0. All right, so this is a special case. Probably end up being, all right, now we can make things work better. All right, because if I want to make if I want to make this work, I can do it. I can make it work. And the way I'm going to make this work is I'm going to say fib 4 of 2. So this is the next sequence number in the sequence. So we're going from 0 to 1 to 2. And this does not have to be a special case. So the solution to 2 is the sum of the previous two Fibonacci numbers. So if I add those two together, I'm going to get 1 here. And then the previous solution, the solution to the sequence number before 2, the solution to the sequence number for 1, that's the previous number that's here, 1. All right, and now I can compute fib of 3. Oh, sorry, the goal is still 4. That is 3. And the solution to 3 is the sum of the two previous. And we're going to take the previous solution and put it here. Whoops, I get that right? Yeah, 3 is 2. I said 3 here, but that's not 3, it's 2. And then 1. And then finally, we'll do fib 4 of 4. And the solution to fib 4 of 4 is we're going to take these two and add them together. That's going to give us 3, and our previous will be 2. Now this is also a special case. These are recursive cases here. But this is going to trigger a base case. And the base case is going to be triggered because the goal, which is 4, and the current value is 4. So we need to stop. All right, so that is a trace of how this would work. And the cool thing is, right, when we stop here, when we reach this goal, if we add these two numbers up, sorry, we don't add the numbers, that's wrong. If we just take the solution here, that is what we're going to return from the function. So when we reach this final state, when we reach this base case, we have the solution by just looking at SOL or solution. Okay? So why don't we try writing the code to make this work. So I'm going to grab this. Copy it. Paste it. And then think about what do we have here? So we've got a base case. That's really easy to do. Maybe I'll take care of that first. So the base case says that if you've reached the base case, just look at the solution argument. That is what you're going to return. That's what the base case is. All right, cool. So let's do that. So we'll put a big cond here. Maybe I'll move that over a little bit. So cond, and if we see that current is equal to goal, then we're just going to return solution. All right. Pretty straightforward. I like it. All right. We also have some special cases here. And the special cases are if we're looking at the sequence number of 0 and we're looking at the sequence number of 1, there's very particular previous solution and previous solution values. This one is bogus. The rest of them are okay, but you just had to get, have something in there to make this work. So, all right. So if current is equal to 0, then what we'll do is we'll call Fibonacci with a goal of goal, a current equal to 1, and we're going to pass in the solution for the solution for 1, which is 1. That is the solution, and the previous solution, which is the solution for 0, which is 0, and that is the call for current equals 0. And then the call for when current equals 1, that's the other special case, we're going to call Fibonacci goal 2. Actually, I think, yeah, let me think about this. Yeah, do we need to do anything else? Let's see, when it's 0, we're calling with 1, 0. If it's, if we're calling with 1 and 0, I think we're actually good. I don't think we actually have to do any more than that. We'll try it. And if we're wrong, we'll make a change. All right, so let's look at the recursive case. So if current is less than goal, then we're going to call Fibonacci with goal, and the solution we're going to then add 1 to current, and then we're going to say, look, in order to get this to work, the solution to 1 plus current, its solution is just taking the current solution and adding it to the previous solution. So our new solution, which is the solution to the next sequence number in the Fibonacci sequence, is is the current solution plus the previous solution. And the new previous solution is going to be our current solution. Okay, so yeah, I think that's pretty good. So let's give this a try, shall we? I have actually written this, and we can take a look at it in just a second. Okay, well, here's our solution put into actual code, and it's, you know, it's not bad. I mean, I think the original Fibonacci solution that uses the stack is probably a little easier to understand, but this one isn't so bad. So keep in mind, the function is carrying along a goal, which is the sequence number that you want to reach, a current, which is the current sequence number that you're currently on, a solution to the current sequence number, and the previous solution to the sequence number that's one behind current. All right, we have to hard code one instance, and the instance that we have to hard code is when current is 0 and you're not at your goal yet, we're going to force a call of Fibonacci with goal, the sequence number of 1. The solution to the sequence number 1 is 1, and the solution to the previous sequence number is 0. So as long as we hard code that, everything else will work. So this is an example of trying out sequence number 5, which should be 5, and I tried out sequence number 8. That should be 21. And there it is, 21. I guess we could put a couple of these in order. Maybe like this. Just do a bunch of them. Just as a couple interesting test cases. So what if we test Fibonacci of 0? That should be 0. Fibonacci of 1 should be 1. Fibonacci of 2 should be 1. And Fibonacci of 3 should be 2. So let's run those. Yeah, this is looking like it's set up correctly. Now remember, the reason why this idea, which is a little bit more complicated than our basic Fibonacci recursive solution, is important, is that we're carrying the solution, the answer to the problem is being carried in these arguments, so we don't need to store them anywhere on the stack. So this will run much more efficiently than the original, more simplified Fibonacci solution.